Hey, what's going on, guys? Let's do this problem right here. This question is asking an 8-meter internal diameter spherical tank made of 1.5 centimeter thick stainless steel, and the conductivity of it is given right here, is used to store iced water at 0 degrees Celsius. The tank is located in a room whose temperature is 25 degrees Celsius. The walls of the room are also 25 degrees Celsius. The outer surface of the tank is black and emissivity is given by 1. And heat transfer between the outer surface of the tank and the surrounding is by natural convection and radiation, right? The convection heat transfer coefficients at the inner and outer surfaces of the tank are 80 watts per meter square Kelvin and 10 watts per meter square Kelvin respectively. Determine the rate of heat transfer to the iced water in the tank and the amount of ice at 0 degrees Celsius that melts during 24-hour period. So the amount of ice at 0 degrees Celsius, and these are the two questions. Now let's go ahead and do the first question, that is the rate of heat transfer to the iced water in the tank. So to find the heat transfer rate, what we do, we use this equation. Q dot is equal to T infinity 1, that is inside surrounding temperature, that is 0 degree. Oh, the thing is here, the initial is going to be outside because the heat will always transfer from hot to cold. So outside is 25 degrees Celsius and inside is 0 degrees Celsius. So this is going to be going from outside to inside. So initial is going to be 25 minus inside temperature, that's infinity 2, and then we have to divide this one by R total, right? We have these two temperatures already, infinity 1, infinity 2. Infinity 1 is going to be the initial, that is this one. Infinity 2 is the final, that is 0 degrees Celsius. And R total, we have to calculate this one. To calculate this, we can draw the diagram of resistance first. So first of all, we have inside resistance, R inside. Then we have R due to this steel, stainless steel. Then we have outer resistance. But in the question they have mentioned that outer, so the heat transfer between outer surface of the tank and the surrounding is by natural convection and radiation. Natural convection and radiation. So we are going to have two resistance right here, like convection and radiation. So we are going to have convection, radiation. So let's say this is our convection, our radiation outside, and that is it. Those are the resistance we have. And this is going to be temperature inside, temperature outside, right? So let's go ahead and calculate this one first. R inside. So inside we are going to have conduction. Actually this is convection, since we have fluid right here. This is a convection. So R convection is equal to, so when we have R convection, we use this equation 1 over HA. So this is initial, let's put AI. So 1 over HI is given right here. This one tank, so inner and outer surface are given by in order. So 8 is inner, outer is 10, right? So inner is what we are going to use, 80. We are going to use 80 right here. And surface area for a spherical shape is going to be 5d square, right? So 5d square, that's what we are going to use. So let's plug the values right here. 5d square inner surface, 5 diameter is going to be, inner diameter is 8 meter, so 8 square. Let's write this on. AI is 5 di square. A outside is going to be 5 d outside square. So here we are going to calculate inner surface area. So this is going to be inner 5d square. And let's calculate this one, and if you plug all the values in calculator, you will get 0.000062 degrees Celsius per watts. So that's going to be the arc convection inside. Now we have, after that we have steel. That's going to be conduction, right? So conduction, let's put our steel. Our steel is going to be equal to, so whenever we have spherical shape, we use this equation for conduction, that is R2 minus R1 over 4 5 K R1 R2. So this is the equation when we have spherical shape. So let's go ahead and plug the values. R2 is going to be outer radius of this steel. So here we have 8 centimeter, and then the thickness of this one is stainless steel is given by 1.5 centimeter. So this is going to be 4 plus 1.5, and that's going to be, actually this is 1.5 centimeter. So 4 meter, we have 4 meter right here, plus 1.5 centimeter. This means 0.015 meter, right? We have to divide this one by 100. So this will give us 0.015, and if you add them together, that's going to be 4.015. So that's going to be the outer radius. So outer radius is going to be 4.015 minus inner radius, that's going to be 4 meter. So 4 meter divided by 4 5 K conductivity of the steel, that's given right here, 15 times inner radius times outer radius. So inner radius is 4 times 4.015, and if you calculate this value, that's going to give you 0.000005 degrees Celsius per watts. So this is hard steel. Now let's go ahead and calculate convection. Our convection, again we are going to use this equation, 1 over H outside, A outside, and H outside is provided right here, that's 10 watts per meter square Kelvin. So 10 right here, and surface area, again we are going to use 5d outside square, 5 times d. D is going to be diameter outside. So we have 8 centimeter, and diameter is going to be different, like 8 plus we have 1.5 centimeter thickness, so this one is 1.5, so we are going to have this one also 1.5. So totally we have to add 3 centimeter to the total diameter in order to have the full outer diameter. So this is going to be 3 centimeter. 3 centimeter is same as 0.03 meter, right? We have to divide this one by 100 to convert into meter, and now this is going to give us 8.03 meter, and now we have to square this one right here. This is going to be 8.03 square. Now if you plug this one in calculator and find the value, that's going to give you 0.000494 degrees Celsius per watts. Now we have our convection, and also they have mentioned we have a radiation also in the outside. So we have to calculate our radiation. To calculate our radiation, we use 1 over H radiation times area, right? But H radiation we have to calculate because it's not provided right here. We have H outside, H inside, but we don't have the H radiation. But we can calculate that one using this equation. H radiation is equal to emissivity times sigma times T2 square plus T surrounding square times T2 plus T surrounding. So this is the one we are going to use. The emissivity for black surface is always 1, so this is going to be 1, and sigma is going to be Stephen Boltzmann constant, that's going to be 5.67 10 to the power of minus 8 watts per meter square Kelvin power 4. And then temperature to outside temperature is 25 degrees Celsius, right? But when we use the radiation equation, we have to always convert that one into Kelvin, because we are squaring this one, so it doesn't work for degrees Celsius. So we have to convert this one to Kelvin. To convert this one into Kelvin, what we have to do, we just have to add. So let's see. Outside temperature. You know what? Here we have to calculate the surface temperature for this one. So to calculate surface temperature, we have to use a different equation. T surface. So let's see. T surface. You know what? Okay, let's assume it's a 5 degrees Celsius and calculate this one. 5 degrees Celsius plus 273, and T surface, T surrounding we already know, that is 25. So we can just add 25 to this one. 273 plus 25, right? T73 plus 25, and if you calculate this value, this is going to give you 5.424 watts per meter square Kelvin. Now let's go ahead and find this value. So here we have this equation, R radiation is equal to 1 over H radiation times area. So 1 over H radiation we calculated, that's 5.424. 5.424 times area. Area we calculated outer surface area, that is this one, same as this one, and if you calculate this value, this gonna give you this part right here. This is equal to 202.57. So we can write this one right here. So without this 10, right? I'm just looking at the area. Okay, without that 10, this value is going to be 202.57, and this is going to be 5.424 times the area. Area of this one is 202.57, and if you calculate this one, that's going to give you 0.000910 degrees Celsius per watts. Now we have this one right here. Now if you notice, we have these two in parallel, these two are in series, but when they are in parallel, we can't add directly, right? We have to combine them together and make this one into series, then we can add them together. So let's combine this one. To find the equivalent resistance, we use this equation, that is 1 over R equivalent is equal to 1 over R convection plus 1 over R radiation. And if you calculate this one, that's going to be R equivalent comes out to be 0.00032 degrees Celsius per watts. Now we can calculate R total. R total is going to be R initial plus R still plus R equivalent, right? And if you add them together, that's going to give you 0.000387 degrees Celsius per watts. Now we have all this information. The main thing is we found the R total right here. This is what we tried to find. because we want to find the Q dot. That's the question, right? Now we have our total, that is 0.000387. Now let's go ahead and calculate this Q dot. To calculate that one, let's raise these parts right here. Okay, let's continue that one here. So we know that Q dot is equal to T infinity 1. So this is initial temperature. We are starting from 25 degrees Celsius because the heat always goes from hot to cold. So hot is going to be the initial. So this is going to be 25 minus 0 divided by 0.000387 degrees Celsius per watts. And if you calculate this one, that's going to give you 64,600 watts. So this is the answer for the first question. The second question is asking the amount of ice at 0 degrees Celsius that melts during a 24-hour period. Now to calculate this one, so here they are asking for the amount of ice. This means mass, right? Mass of ice. So mass of ice is Q over HIF. HIF provided right here. We have to find the Q. In order to find, we have Q dot. To find the Q, we just have to multiply this one by time. This is same as joules per second. And if you multiply that one by time, second cancels, you will end up with joules. Let's go ahead and calculate Q. Q is going to be equal to Q dot times delta T. And they have mentioned this is 24-hour period. And in 1 hour, we know that it's going to be 3,600 seconds because we have 60 minutes. Each minute contains 60 seconds. So 60 minutes times 60, that's going to give you totally 3,600 seconds in an hour. So here we have to multiply this one by. So let's convert this one to kilojoule, 64.600. Because we are dividing by 1,000 in order to convert into kilojoule. Kilojoule per second. Multiply by delta T, that's going to be 24 times 3,600. And if you multiply, that's going to give you that, that's going to give you 5.581 times 10 to the power of 6 kilojoule. Now we have this value. Now we can go ahead and plug it in this equation. So we have 5.581 times 10 to the power of 6 kilojoule divided by HIF, that is 333.7. 333.7. And if you calculate this one, that's going to give you 16,730 kilogram. Now the surface temperature, we have assumed this 5 degrees Celsius. Now let's go ahead and find this one using this information and see what we get. So from this one we can find, so let's trace some of these parts. Okay, now T surface. So let's put Q dot equation. So this is the answer for the second part, 16,730 kilogram. So we have done those two parts. Now let's analyze this surface temperature, 5 degree. So this one Q dot is equal to H convection plus radiation A outside. So I'm just looking at the outside Q dot and analyzing, right? So T infinity 1 plus T surface, and this is going to be H convection, that is, so we are trying to find surface temperature. Ts is equal to, if you rearrange this one, that's going to give you T surface, T infinity 1 minus Q over H convection plus radiation times A outside, and that's going to be 25 out, this is initial, minus Q, that is 64,600 watts. We calculated that one right here, divided by H, convection plus radiation. So that is 10 plus the one we calculated, 5.424 over 202.57. This is the one, right? Area. And if you calculate this one, that's going to give you 4.3 degrees Celsius. So this is approximately almost equivalent to this one, right? Because we are converting this one into Kelvin, and this is almost same as this one. Kelvin means we are adding 273, and when you have 273, this small 0.7 doesn't make much difference. So we can assume that this is same as this one. Therefore, we don't have to go ahead and change our calculations, because both of the this is almost correct. So we can neglect this small difference, and we can say this is the correct calculation, right? And that's how we do this kind of problems. I hope you guys find this video helpful. See you next time.